Okay, so good afternoon, everyone. So today is the second lecture of the hypothesis testing procedure. Today, we're going to talk about the outcome that we are interested in as a continuous variable. And instead of comparing one mean to a number, which is one sample mean, we're going to compare two samples, or another word, compare two means. But at the same time, we're going to talk about dependent sample. Dependent sample is the same sample where we took two measures, like before and after. Or if we take a male and then we match that male with another male and we take some information. I'll talk more about the dependent sample when we reach there. Just to remind you of the learning objective, I did not repeat them. So we are in the hypothesis testing. I think we need to mute all. All are muted. Okay, so you are all muted. Good. So we are, so again, hypothesis testing is one of the procedure for making inferences. And we defined the null and research hypothesis last time as the null being the no difference hypothesis. It means that if you expect a relationship or if you expect that your population mean equal to a certain number, your null would be, yes, it is equal. Your alternative hypothesis, or what we call research hypothesis, is the one with the relationship. We talked about the statistics, level of significance, and decision rule, type 1 and type 2 error. And then we explained last time the difference between one-sided or two-sided test of hypothesis. And now we are going to do the testing when the outcome is continuous and the variable, and we are comparing not one sample, but two samples.
Hello, Professor.
Yes.
I'm Lara. I just wanted to say that I'm with Kinda watching the online
Okay, so let me write it down
class because my laptop is off.
That's good. It's good. So Lara with Kinda, because I'm taking the attendance from Zoom.
Okay.
Lara and Kinda. Thank you for notifying me. Thank you. So the new scenario today is my outcome is continuous. Last time we looked at, if you recall, continuous and categorical. So we look at, for instance, the mean body mass index or the mean cholesterol of a population. We take a sample and we compare to the mean. And then we also take a proportion who are smoker. We compare people who are smoker, and we took a sample, calculated the mean, and then compared it to mu. Mu under H0 was a certain number we call normative number. So today we are taking again, all today, so this lecture is about outcome, which is continuous. It could be systolic blood pressure, weight, cholesterol, body mass index, and dealing with the first scenario is dealing with two independent study samples, meaning that if I collect data, I have a population of AUB students, so AUB student is my population, and I want to look at if there is a difference in body mass index between male and female. Okay, so what I do, I take a sample. Okay, so I do a cross-sectional study, remember, cross-sectional study. I collect data on gender, of course, on many things, so male, female. And at the same time, from all the male, I collect data on body mass index for the male and for the female. Okay, so these are two independent. So I go, whoever student I find, I ask about gender, and I measure their weight and height. So what I get from the male, from the data, I get an X bar of BMI among male and an X bar for female of body mass index. So these are called two independent study sample. These study sample, I use them to check whether the population of male is different from the population of female. So the data I get, I do a cross-sectional study. I collect data on gender, male, female. So for everyone, I measure the outcome, so the male and the female, and then I would have an N1, which is the male, with their mean BMI and the standard deviation. You know that every time we calculate a continuous variable, its distribution, what we do is we summarize with the mean and we take the standard deviation. The S1 squared is called, if you recall, the variance. Okay. And then for the male, I will have another sample size of n equal 2. It doesn't have to be equal. So you can take a sample of 1,000 AUB students. You might end up with 600 female and 400 male. These are two independent samples. So N1 is 600, N2 is 400. You collect the data from the male and you collect the standard deviation. So that's the new scenario. So that new scenario, another example would be if we're doing a clinical trial, meaning that we're doing an experiment in the lab, and then I have a pool of patients who actually agree to be part of that clinical trial or experiment. That pool of patients, I divide them into a patient who would take treatment 1, and we look at the mean treatment 1, let's say what their blood cholesterol would be after I give them treatment 1, and what would be their blood cholesterol when I give them treatment 2, a separate. So I divide my population who are people who came and said, yes, I want to be part of the experiment, into a group that take treatment 1 and the group that take treatment 2. They are very independent of each other. And then I calculate a mean. It could be a mean of cholesterol, HDL, and then here a mean 2 of HDL, and I compare them. Another one could come from a cohort study. So a cohort study, remember what's a cohort study? It's a group of people that I collect data on baseline, and then I follow them up. So let's say those people are makes up two groups, a group that's exposed to war, and not exposed to war. And then I want to look at their mean depressive symptoms.
Professor?
Yes.
Hello, I'm Tamara
Yes.
Al-Miqdad. I'm with Lynn Hasham. Sorry, I'm cutting you off, but because you didn't see my hand,
Okay.
but because we're on campus, so we entered from the same laptop.
Okay, so Lean, you could have told me late, Mali. So Lean, we are with who?
Lynn Hasham and Tamara Al-Miqdad on the same laptop.
Okay, Tamara. Okay,
Thank you.
okay, sure. Sorry. Okay, so ladies, it depends on the view because I barely see the participant. Maybe I should put the participant on the side. I'll put it on the side so I can see if anyone is, okay. Now I see you all. You're 24. All right. So as I was saying, another way of getting two independent sample could be a cohort study. Again, this is something that you have for your midterm or your exam 1. So a cohort study is a group of people. You collect data on, they don't have the outcome, and then you follow them up to see how many will have a certain disease, how many will have a certain number of depressive symptoms, or actually mean of depressive symptoms. So exposed to war, non-exposed to war, this is group 1. Each one can be n equal, it could be 100, here could be n equal 500. It doesn't have to be equal again. And then you follow them up to see what's the mean number of depressive symptom in 1 and the mean depressive symptom in 2. Again, these are independent sample, all right? So they don't depend on each other. So being in group 1 or in group 2 does not depend on being or having particular characteristic that's in group 1. So just you go, you have a questionnaire, you ask, have you been exposed to war? Have you been displaced? Yes, no. Have you been displaced? Yes, no. And then you will end up with two groups. These are called independent group. Okay. So this is another example. Okay, so what's the test of hypothesis for two sample where the outcome is a mean? So we're talking about a continuous outcome. Okay, it is systolic blood pressure, again, BMI. Okay, it's two independent sample, like the example I gave you. You have a group of patients. You give one group treatment 1, another group treatment 2. You do a cross-sectional study. You have a number of male in your sample and a number of female. And each one you ask them, you weigh them, and then you compare their mean. Okay? And what would be, so do you remember what are the steps in hypothesis testing? So first is set your hypotheses, right? Okay, anyone, okay, I have to also monitor the chat, anything in the chat? Okay, no, nothing yet. So one, I set my hypothesis H0 and HA, we call them, okay, or H1, okay. Then, remember what we do second? Decision rule, which is alpha equal 0.05 or 0.01. And then 3, you do your test statistics. And then you compare your test. So you find the Z for your test statistics or T. And 4, you compare the test statistics, the Z for test statistics, with your decision rule. And then you decide whether you want to reject H0 or keep H0. So we continue. So two independent samples, sorry. Okay, so this is the steps, continuous. We set up H1, H0 equal mu1 equal mu2. It's always the null hypothesis is the mu1 equal to mu2, like the mean BMI in males is equal to the mean body mass, BMI in female. We're talking about the population, right? Mu is for the population. H1 can be mu1 greater than mu2, could be mu1 less than mu2, or could be mu1 different than mu2. This we call it two-sided, and this is one-sided, okay? And how do we decide whether it's one-sided or two-sided? Anyone?
Based off of the question, right? It says if
Excellent.
it's,
Yeah. Yes, thank you.
if
Thank
it
you. So it's-
decreased or if it's different in general.
Exactly. So it depends on the question. So if the question of the research is there a difference in body mass index between male and female? It's simply mu1 different than mu2, but always H0 is mu1 equal mu2. But if the question is treatment 1 and treatment 2, is treatment 1 give me lower values for blood pressure, for cholesterol than treatment 2, then it's mu1 minus less than mu2, which is one-sided. So as you rightfully said, it's all based on whether it is what the researcher want, and the way we want to answer our question. So we said the first one is, so this is the first step, is the test. This is first. Second is the test statistics. So what's the test statistics for when we have two means or difference in means? So the test statistics is depends on the sample size. Okay, so we have two formulas. Okay, so if N1 and N2, both of them are greater than 30, my test statistics is X bar 1 minus X bar 2. So what we do after we set the hypothesis, we collect the data and we measure X1 and X2. So we measure, so data, and then we measure X bar 1, X bar 2. We have S1 and S2, and the test statistics is X bar 1 minus X bar 2 over the pooled standard deviation. We call it pooled standard deviation. We'll see how we calculate it. And if you recall, we used it for the confidence interval. Do you remember the pooled for confidence
Yes.
interval? Great, Nisreen. Thank you. Nisreen, you're the voice of the class, it looks like. But I'd like really to hear everyone, even if you're not sure about the answer, just say it. So the pooled square root of 1 over n1, 1 over, what do we call this? This component is called the standard error of mu1 minus mu2. That actually we calculated it in the confidence interval of mu1 and mu2. You can go back to the confidence interval. So this is if my n1 and n2, both of them are greater than 30. Okay, so then the normality assumption is met, and I'm fine using z. Okay, z equal x bar. So, and then if n one of the n1 or n2 or is less than 30, not less or equal, then my test statistics is not the z, but a t-test. So I use a t-test for at least one of the n less than 30. It will be the same. Okay, x bar 1 minus x bar 2 over sp of 1 n1, okay, plus. Okay, so this is my test statistics. So what would be next? Okay, is since we are talking about the test statistics, is to calculate n minus 1. And I don't know why on my, do you see the plus and minuses?
No, they don't show.
I don't know why it's not
Professor,
showing,
I
but
wanted
in
to
the
ask-
handout it's showing. In the handouts, the plus and minuses are showing. It's only when I project them. I don't know why. So
What's the sign of 1
Oh.
over n in the previous slide?
okay, I put it plus 1
Plus,
over
I
n1
didn't
plus 1
notice,
n1.
sorry.
Okay, it's no problem. Okay, I really apologize because I checked the handout yesterday and all the signs are there. So n minus 1, so s pooled equal n1 minus 1 s1 squared. And again, this is something that we look, if you recall, in the 95% confidence interval of mu1 minus mu2. Okay, plus n2 minus 1 s2 squared. These are the variance, plus over n1 plus n2 minus 2. Again, recall that this component is called the standard error of the means. Okay, S is the standard deviation of a sample. S over square root of n is called standard error of the sample mean. Okay, and S is the observation standard deviation. Okay? So once this is done, the second one is, so let's see the example. So this is the test hypothesis. Again, I would like to again clarify that those formula, you don't retain them. You don't have to memorize them. They will be given in a formula sheet once during the exam. You only have to really understand which one you have to use and when is it used and how to interpret the result. So this is an example. So we have a clinical trial. The clinical trial was done to look at whether a new drug is better than an old drug in lowering HDL cholesterol. So patients were randomized. So they were divided in a random manner. So one group is to receive the new drug. So this is N1. And another one, or placebo, we call it, that is either not taking or taking maybe the old drug or the regular type of drug. And on both groups, we measure total cholesterol, not only HDL and LDL, total cholesterol. So the question is, do we have enough evidence that the new drugs actually have a significantly reduced cholesterol compared to the placebo or the old drugs? So what we're looking at, we want to look at the mean total cholesterol for the new drug, and compare the mean total cholesterol compared to the placebo. I think I wouldn't give nothing to patient, but I would give them maybe the old or the regular one that they take, and we'd like that mu1 to be less. Why less? Because we're talking about reduction in cholesterol, right? So we expect that the cholesterol will be less in the new drug compared to the placebo or the old drug. So these are the numbers. So in that clinical trial, we had 15 who were put on the new drug, 15 on the placebo, the mean cholesterol was 195 milligram per deciliter, I think, with 2 to 7 for the placebo with the standard deviation. Right? So this is X bar. So these are X bar, and this is S. So what would be H0? Mu of nu equal mu of placebo. And your research hypothesis, we call it research, we call it alternative hypothesis. Okay, based on the handouts, it's always called H1. It's fine, we can always call it H1, but it is my research hypothesis. This is what I'm trying to prove. I want to prove that mu of nu is less than mu of placebo. Okay, so this is one-sided. Okay.
Professor,
Yes,
I don't
Yes.
know what to do when I want to write the H1. Like when do we use the one-sided? When do we use the two-sided?
okay, so what was the question? So the question is there evidence of a statistically significant what?
Reduction.
Reduction.
So we
If
look
the
for
question-
keywords.
Yes, keyword. So if the question is, are the two drugs similar in terms of reducing cholesterol? So we're not questioning which is better, which is reducing more.
Yeah.
So I would say mu of the new different than mu of the placebo. So all depends on the research question that you are after. Sometimes you're doing research and you want to prove, let's say, that the female has higher depressive symptom than male. So you
Yeah.
collect the data, and this is actually what you want. It's because you know how this is what you are hypothesizing, because we know that female maybe react more to stress, etc., while the male maybe they have more personality stuff. Okay, so mood disorder are more among female, and that's why I expect female to be higher. So then you put it aside. If you don't know, you say, is there a difference between male and female? The mere question of, is there a difference? This means that it's a two-sided. Are they different? Is there a
So we
difference?
ask, are they different? And then we choose.
No, and then you see the data, of course. I mean, the
Yeah.
way you state your hypothesis, when you say, is there a difference? Your hypothesis would be two-sided.
Okay, deal.
It means
How much?
you are whether they are less or greater. This is part of what you're saying and what you are accepting.
Okay, thank you.
So for this example, actually we have a one-sided. My decision rule is alpha 0.05, and my test statistics T. Why is it T? Because N is 15, and 1 and 2 both are less than 30.
Less than 30.
Okay, less than 30. Okay, so T, when I say T, it means what kind of distribution I'm using?
The T table?
A T distribution, a normal distribution, right? To
Yeah.
use a T or a Z, I'm assuming that this is normal. The distribution of mu1 minus mu2 is normal. So I convert. So what I'm doing here, look what I'm doing here. X bar 1 minus X bar 2 is the absolute difference between those two, right? مظبوط. It's 2 to 7, or actually 195. It doesn't matter. So it's 195 minus 2 to 7. Okay. So 7 might feel equal. And the one, and so this is around 38, right? No, sorry. It's 32. Sorry. It's minus 32, right? So in the cholesterol, the difference is 32 in terms of absolute number. But if I standardize to know how far is it from a T equals 0 in terms of standard deviate, so now you using your T table. So this would be, so first it's it's minus 1.701. So this is 195 minus 227 over SP that we calculate. We'll see the SP. Did we calculate it here? No. So it's not calculated yet. So this is the SP equal is 29.5. Sorry, the SP is 29.5. So it's 29.5 square root of 1/15 plus 1/15. This whole T is equal, it's not equal to anything. Okay, so let me rewind. Okay, and forget about those numbers. So we did the test statistics. We'll see the calculation and the following slide. The third step always is a decision rule, right? So the decision rule is based on the T. Remember how we find the T in a T table? We look at first the degrees of freedom. So the degrees of freedom when we have two samples is N1 plus N2 minus 2, which is equal to 28. So I would look at the T that correspond to 28 and alpha equal 0.05. So it is minus 1.701. So this is my decision rule. This means that any value of the test statistics, any value that falls less than minus 1.71 is reject. And any value that is greater than minus 1.71 is to accept H0. So this is H0. All this is H0. So what we do, to do an SP, to do a pooled variation, we check
Wait,
first.
Professor,
Yes.
the
Yes,
minus 1.701 is from the T table, right?
Yes, and
Based off of the
I
degrees
should
of
have,
freedom?
yes, I should have it. Yes, I should have the Z table in front of me. Do you have the
Yeah.
Z table in front of you?
No, but isn't it on Moodle?
Bella, you have it, but I mean, if you have it like next to you or something, I will be printing those T table and you have them during the exam. So you'll have next
Yeah,
to you
okay.
the T table, the Z table, and all this list of formulas, okay?
Okay.
Okay, so the ratio of sample variance, do you recall also how do we test whether the variances are equal? Anyone from the confidence interval? If we take
Do you
S,
mean like if the assumption is reasonable?
yes, so it should
Yeah, it
be
has to be between 0.5 and 2.
excellent. So it should be 0.5 and 2 exactly. Sorry. So here, what's the ratio is 0.9. So do you remember, ladies and gentlemen, this about equal variance?
Yeah.
Okay, Nasreen, thank you, Lava. You gave the answer. So, okay, so whenever we want to compute something called pooled, this is called pooled standard deviation. Okay, to do a pooled standard error, excuse me. So to do a pooled standard error, I have to first check that those S1 and S2 are equal. Their variances are equal. And to see whether their variances are equal is to have a ratio of S1 squared over S2 squared. If it is between 0.5 and 2, therefore, we can go on and do this S pool. If this is not equal, there is another formula, but you are not responsible for. So as long as we have those ratio, justified or tested for, so you use the SP. So the SP is N1 minus 1 S1 squared plus N2 minus 1 S2 squared over N1 plus N2 minus 2. These are called your degrees of freedom.
So Professor,
Yes.
if the ratio of sample variances is outside of that, between those two numbers.
There's another. So sometimes one is that there are two ways of doing it, is doing another formula and using directly S1 squared plus S2 squared. So not do the pool, or just do something that called non-parametric test, meaning we don't use all the T test to Z test are not used. So there are other alternative tests when your sample is not normal and your variances are not equal. Okay, but we're not getting into that. So we're only getting into, or we're looking at where the ratio of sample variances meet the requirement to do a pool. Okay. And we're not taking any alternative, but thank you for your question. Yes, there are alternative ways and alternative formulas. So for now, we're taking the S pool when we have a t-test. So the SP is 29.5, and then we do the test. So how much is the test? So the test is T equal X bar 1 minus X bar 2 over the S pooled again. So again, this is the standard error of mu1 minus mu2. And this is minus 0.292. So minus 2.92. Y is 195 minus 227. So what would be my decision if I again put the minus 2? So what's my decision rule? Any value less than minus 1.701 is to reject, right? Based on alpha 0.05. So where is my minus 2.92?
It's
It's
in
here.
the rejection, yeah.
It's in the rejection, exactly. So therefore, sorry, 2.92. So therefore, what would be my conclusion? Reject H0 because minus 2.92 is less than 1.701, minus 1.701. Oh, sorry, it's on the second, it's on the second line. So we have statistically significant evidence. So this is how we interpret. We have statistically significant evidence. Why statistically? Because we did a test of statistics. Why is significant? Because it falls here and its probability is very low. So we have statistically significant evidence at alpha 0.05 to show that the mean cholesterol level is lower when we use the new drug. I can state it differently, and I can say that the new drug statistically significantly reduces cholesterol compared to placebo at alpha 0.05. What's the probability of 2.92? It's when you find the T or the Z. So I look at this in the T table, T of minus 2.2 or 2.2. And then I look at my T table, I look at the degrees of freedom of 15 plus 15 minus 2, which is 28, and I find the P value corresponding to P less than 2.92. So if my T falls here, what do you expect to be less or greater than 0.05? If it's here, what would be that probability?
Less.
It will be less than 0.05, but actually it is less than 0.005 based on the t-test. It means that if this is all my H0, so it means that it is very unlikely. It is very, very unlikely or very low probability that the two means are equal. And therefore, this is another evidence to say that, yes, the new drug actually is very different and it does reduce the cholesterol more than the placebo.
Professor,
Yes,
can you go back to the previous slide?
yes, the previous slide.
Yeah, the one with the pooling. I
Yes,
got
yes.
lost when you were explaining the sample variance and how they help with pooling. I got lost by the examples.
Okay, so that's it. So what we have is, this is the test statistics for, and I'll go back to show you the first test statistics. Okay, so
Okay.
always when we're doing the test statistics for two means, it's S pooled over 1 and 1 plus 1 over N2. And actually the S pooled is mostly used when we have T small t. Okay, why? Because when we have a small t, the standard deviation are not very good estimate of the population mu. S is a standard deviation of sample that we use to estimate that of the population. Usually when the numbers are small, just using the S instead of the sigma does not actually give you a good estimate of the variation. So in order to correct this, we do something called pooled. Yani we pool the standard deviation of the two samples. How do we pool them? We pool them by this formula. So
Okay.
what we do is in this formula, we replace the S's by an S pool. Where
Like-
is it coming from? But if I may, it's coming from that formula where we put n1 minus 1 s1 squared, n1 minus 2 s2 squared over n1 plus n2 minus 2. But how? When can I use this? I can use this formula only if the ratio of s1 squared over s2 squared, okay, is between 0.5 and 2. So if the pool, this one, S1 squared over S2 squared is between 0.5 and 2, this means I can pool the standard deviation of the two samples.
We always can pool, right?
We can always pool, yes, of course, but
Okay.
but to pool, لا, always can pool. We want to pool if the assumption of equality is had. So, and how to check and they are equal by this ratio. So we have to assume equal variances, sigma 1 squared, and to do this, we check the ratio. If the ratio is between 0.5, so your assumption is reasonable. So Nasreen asked, or someone else asked, what if they are not? So if they are not, we have to use another formula, okay?
Okay. Thank you.
That's it. So we have to use another test, statistics, another formula. So now we have tested the ratio is 0.9, which is within the range, and therefore we did an S pooled, which is 29.5. We replaced the S pooled in this formula as 29.5, and we get minus 2.92. We compare it to 1.7, and therefore we decide to reject because it falls in the rejection region based on, this is all the 0.05, and my test is here. Okay, so I set my hypothesis, I decide on the decision rule, I conduct a test statistics, I compare my test statistics to the critical value, 1.7, and then I do my conclusion. And I can then compute the P or find the P value of my test statistics. So the P less than 0.05 is the P associated with minus 2.92. This is another scenario. So the other scenario now, so this is for independent sample, okay? But anyway, for samples that are N1 and N2 greater than 30, it would be the same. Sometimes I want to tell you something, which is not in the lecture, but when N1 and N2, both of them greater than 30, the difference is what? We use what? Z,
Z.
right? So Z is again X bar 1 minus X bar 2. But since it's not in the lecture, I don't want, but I want you to know, over square root of S1 squared over N1 plus S2 squared over N2. So we don't have the pooled, okay?
Why isn't it in the lecture?
I don't know why it's not there. It's not put in the lecture.
Okay, I'm
Honestly.
gonna write that down then.
Okay. I don't know why. I don't know how I can directly. Anyway, so forget about it. So we're talking about the Z pool. Okay, so I will look into the formula sheet. If in the formula sheet there is this kind, the only difference is what? First, you use the Z, if N1 and N2 less than 30, and you don't do this S pooled, you only do S1 squared plus S2 squared over N1, S2 squared over N2. Very simple. I'll check it out and let you
Not
know.
1 over N1, it's S over N?
No, I'm going to check, okay? Okay.
Okay.
I have to check it out. At least my recollection is that we don't do the pool when N is less and 2 greater than 30. But if you do the pool is fine. So it's okay to do the pool, because when we do test statistics on any software, there's always an issue of testing whether the variances are equal. So I would say always test the variances are equal and do the pool. But sometimes if n and n2 are greater than 30, the S1 and S2 are good estimate of sigma. But if they are too different, there might be a problem. So that's why we do the pool. So again, let's focus on that. If the N1 and N2 are greater than 30, what should we do? Is use the Z, okay? Not use the T. So now another example, new scenario where the outcome is continuous, like again, systolic blood pressure, weight, cholesterol. But instead of having two independent samples, we have two matched study samples. What is a matched sample? It's like I take, if I want to do, to see if exposure to war is important in predicting depressive symptoms between male and the depressive symptoms. So what I do is for every person. So let's say I find someone who's exposed to war who's a male. So male exposed. I would pick up male unexposed. Male then was 15 years of age, and here also male 15 years and unexposed. And then I compare the exposed to the unexposed. So in this case, because my unexposed were matched to my exposed, this is not an independent sample. Another example of dependent samples or matched or dependent sample, I want to call it dependent sample, is take a group of people, give them a drug. Okay, now take a pool of people, measure their blood pressure, and then do an exercise for the same group of people, and then measure their blood pressure after the exercise. So before and after. So I have an N1 and N2, but those N1 and N2 are the same. So it's the same group of people I take measurement on. Okay, I do my intervention, and when I'm done with the intervention, I measure their blood pressure. So the two measurements are not independent, they are dependent. So this is another example of the new scenario. Either matched, yani when I pick up I pick up a girl who's taking drug A, I can take another girl who have the same age but not taking drug A. So this is what we call matched study sample. So on each participant, I measure outcome under each experimental condition. We don't compute a mean difference. We don't compute X bar 1 minus X bar 2. We compute the mean difference. So for everyone, I find the difference between time 1 and time 2, between this male and this male, and then I average the difference. I don't average what's the average male and what's the average male and this. I look at the difference and then I average the difference. So I compute differences between X1 and X2, between before and after, and then I would have only one N, one mean of the difference and standard deviation of the difference. Let's see how it does, how it works. So we have a certain number of people. This is N. The same person, one, I measure him or her, so I get a 55. The same person I measure after a while, and I have another measure. So I don't have an N1 and N2. I have a difference between N1 and N2, which is here 15. Okay, it depends as I'm looking measure 2 minus measure 1 or measure 1 minus measure 2. So let's say I'm taking measure 2 minus measure 1, it's 15, and this is here is 18. Okay, so I have the same people, and I'm taking the measure on the same people the first time, the second time. Or I can have two groups of people, but they are matched. Matched meaning they share very many common characteristics, but one of them are exposed to war, another are not exposed to war. Okay, so measures taken serially in time or under different experimental conditions. It's like in a crossover trial, so we have eligible participants, you give them treatment and you see what happens, then you change to placebo. And then the other people, it's the same. You give placebo, then you see the treatment. So it's the same people, but given two types of treatment. So each participant is measured on the same, on treatment and placebo. But the most important, I would not, confuse you, or this is a bit advanced, the crossover trial. I would say the best example for dependent sample is when you do a before and after experiment. The same people, you take their measurement on the outcome, and then you do your experiment on the same people you measure at time 2. And matching is another one, like every person. If you take a case of autism, this person is 10 years old, male, and you want to look at their score on IQ score, then you take another person who's a male, who's 10 years of age, and you take the IQ. When you compare this male to the other male, they are not independent, they are dependent. So you consider them as one person and you look at the difference between those two and not the mean of all those who are autistic compared to those, who are non-autistics. So here is an
Wait.
example. Yes.
So it's not like you take a person, for example, who's autistic, and you take a test before, and then you do an intervention, and then take the same test for the same person.
You use the same type of testing. You can do it different ways. Okay, this is an experiment. So the experiment can be, let's say that you know that there is a cognitive behavioral therapy, CBT, is good for improving the performance of autistic child. Okay, so what you do is you take the mean IQ before the CBT. Okay, and then you compute for everyone, X1, X2, X3 for the autistic. Okay, and then you intervene with CBT. And then after the intervention, X1 would have, so here you have, let's say, IQ X1, here would be X11, and here X12 here. So this is, you cannot take the mean of those and the mean of those before and after, but you take the difference of each one. So that's before and after. If you want to have it matched, it's another example. No, you take a group of autistic that did not take any type of therapy, right? So you take 1, 2, 3, no therapy, 1, 2, 3, no therapy. Okay, how do we match them? Let's say one is 10 years male. The second one is 5-year female. And the third is 6 years male, female. So you can either take them before and after therapy, or find a group who are taking a therapy, so therapy, another group, but where your first would be 10 years male, but no therapy. 2 is 5-year, but no therapy, female. And the third is 6-year and female. So these are matched, right? Matched. They are not independent. So the people who don't have the therapy are not independent of those who don't have therapy, because we match them by age and gender. So therefore, I cannot use X bar 1 minus X bar 2. So you have to be very careful to what we give you as a given and a problem statement, how you design. So if the design is matching or dependent sample before and after intervention on the same people, this is what we call paired or matched. So I'm pairing, this is paired. Okay? So how do we state the hypothesis?
So,
yes.
but it always has to be 2 different samples, even if they're matched.
Of course.
That's what you mean. Yeah,
Yes,
okay.
you can have 3 groups, but usually 2. Yani you take a group and you match the other group based on some characteristic, gender, age, etc.
When there is
Okay.
pair and match, we use the old equation.
No, when you don't have, well, when you have.
When we have pair and
When you
match.
have pair, you don't have any more mu1 minus mu2. You cannot consider this a mean, separate mean, and this is a separate mean. No, you consider the difference for every person. You look at his before and after, and then you average the differences. So therefore, your hypothesis is H0. The mean of the difference is 0 in the population, and HA or H1, the mean of the difference is either greater than 0, the mean of the difference less than 0, or the mean of the difference different, and then, which makes sense. If you don't expect difference between no therapy and therapy, what would be the values of the IQ? The same, right?
0?
Yes,
Or,
the
yeah, the
difference
same.
would be 0. Yes, they would be 0. Because each one would have, if you take this one minus this one, would be 0. So if you average these, so you expect that if there is no difference between the two, or this therapy is not working or working, that under the null hypothesis of not working, it means the mu of D is equal to 0. So the average difference is 0, or the average difference is greater, less than 0, or different than 0. Similar to everything. So my Z, so I do the test statistics for n less than 30. We know now. We use the Z, and for n less than 30, we use the T. Do we consider N1 and N2? No, we consider only 1. So even here we have 3 no therapy, 3 no therapy, and 3 therapy. The sample is only what? Not 6, 3. If I have a before, 5 people, I measured before, and then I measure after, the N is 5, it's not N, N1, N2. So my Z statistics is X bar of the D, so the average difference that I compute from the data, minus what's mu of D under H0? Remember, I said always we assume H0 is true. Always we do assume H0 is true. And then I see how far is the average that I compute from a mean of 0. Okay, and the standard error for the average difference is standard deviation over square root of n. And similar, if n is less than 30, it's the same t statistic. However, we will be generating z instead of t only when n less than 30, and when n greater than 30, it is z. Remember the z, we find the critical value. Remember what's the alpha of 0.05 or 95%? Z is 1.96.
1.96.
If it's one-sided, it's 1.645. If it's two-sided, it's 1.96. And for whatever t, the t is, we have to look at the degrees of freedom, which are here, n minus 1, because we are only dealing with one sample, not two samples.
Professor, just to make sure if I understood it well, when there is a pair or match, we find the difference between the X bar and we use that in the equation.
Not the X bar, the X, the
Okay.
observation. X bar is a mean. We find a difference between individuals, individual measure. Yani, I measure someone at time 1, he or she gets a certain level of blood cholesterol. I measure that person in time 2, and I find a difference for that person, which is X. So the observation is not anymore the actual value of the cholesterol, it's the difference in cholesterol between time 1 and time 2.
Okay, thank you.
Okay, sure. So now it will be clearer in the example. So the example is there a statistical significant difference? So what do we say? Difference. And mean systolic blood pressure. So I'm looking at SBP, systolic blood pressure, which is continuous, measured at exam 6 and 7 approximately 4 years apart. It means that I have time 1 and time 2 of the same people. Time 1 is exam 6, which is exam 6, whatever, 6. And then after 4 years, I measure T2. And here is SBP for subject 1, 2, 3. And then I'm looking at X, X2, X1, X2, X1, X2. So I want to see the what? If there are differences in mean systolic blood pressure measured between those two time periods, yani 4 years apart. Exam 6 and exam 7, but let me tell you that Framingham study, which is a big cohort, they have several time points of data collection. So every like 5 or 10 years, they do a big survey. But here they have 2 surveys that were done exam 6 and exam 7. So it means that it's the 6th time that they measure the blood pressure. So they want to see between time 6, exam 6 and 7, which are 4 years apart, whether systolic blood pressure is changing. So they took N 15, so this is N less than 30, right? And then the mean difference was minus 5.3. This means that here, let's say systolic is the high or the low systolic. I think is the low, right? Then all they had like 80 mercury. This is 82. Here was 76, and here is 70. And then 80, for instance, 90, and here is 88. And then the difference is, okay, 82 minus 80, 70 minus 76, 88 minus 90. So you have to be consistent. So I'm taking 2 minus theta and 1. And then we average those differences. Okay, so the 2, this is 2, this is minus 6, this is minus 2. So minus 2 minus 6 plus 8 plus 2. And then over, what's the total sample size? 15. And then they found a minus 5.3 this is D bar, which is the standard deviation of the sample is minus 5.3. Okay.
So
it means
basically they just already gave us all the differences, right?
Yes, so yes, but I'm telling you how you get it. How did they get the differences? So for every person, they look at time 1 and time 2, exam 6 and exam 7, they average the differences. So the difference is a negative differences. So people's systolic blood pressure, the mean is minus 5.3, so negative, which is between 6 and 7. And then the standard deviation was 12 point with S equal 12.8 units, which is, so difference were computed by subtracting 6 minus 7. Okay, so this is D is 6 minus 7. So time 1 minus time 2. So they find that the systolic blood pressure is negative. So what we do, so this is the test of hypothesis. So mu equals 0. It means that I hypothesize that the mean difference in the population of offspring of Framingham is 0, so no difference or difference. So there was a why two-sided, because the question is there a statistically significant difference, right? We did not say, is it reduced after 5 years? We're only checking the differences. So this is two-sided. And two-sided is important because it means that the 0.5 is 0.025 here and 0.025 here. So I'm rejecting whether they are here or whether here. And this is H0. Okay, with a mean of 0. So alpha is 0.05. So, and on the two-tail, I reject. The test statistics, Y is T because N is less than 30, right? So it's X bar D, which is minus 5 point, what is it? 5.3 minus 5.3. So minus 5.3 minus mu of D under H0 is 0 over the standard error. Oops. Sorry. Oops. No, what happens? But sorry, I don't know what happens. Okay, I apologize. I don't know what happened. So we have n less than 30. So the test of statistics is the mean of the difference in the sample minus the mean of the difference under H0, which is 0, over the standard error of the difference. This is called standard error of D. So the decision rule, because it's T, it is associated with n minus 1 degrees of freedom. So therefore n 15 minus 1. And I have to look into the T table, and the T under 5% one-sided is T of 2.145. So I would reject if the value of the test is minus 2.145 or plus 2.145. So any value of the test that falls either here or here is to reject. So let's see what we got. So the test statistics is again T, and then it's X bar minus 5.3 minus 0 over 12.8, which is the standard deviation, over square root of 15, which is equal minus 1.6. I'll see it on the T. So my T here is minus 2.145, and here is 2.145. Where does this falls? Where does it fall? Is it outside? Is it less than 2 point?
Side.
It's inside. Minus 1.6 is here. So therefore,
So it's not rejected?
it's not rejected. So I don't reject H0 because the minus 2.145, the 1.6, excuse me, lies inside between the minus 2145 and the plus 2145. So therefore, we don't have statistically significant difference evidence at alpha 0.05 to show that there is a difference in systolic blood pressure over time. So in the Framingham study, I don't have a change in systolic blood pressure between exam 6 and exam 7. No difference, no statistically significant difference because I have run an analysis or test of hypothesis. And that's it. Okay, so if you want to, so again, if this was 30 or 40, if my n, okay, so if my n was 40 and I have the same difference and standard deviation, it simply would have been z equal minus 5.3 minus 0, which is mu of, this is mu of d under H0 equals 0 over 12.8 over square root of 40. So let's do it. If we have a 40 standard deviation, so let me do the math. So this is 5.3 over divided by 12.8. Okay. Times. I'm doing it. You can do it with me, Elizabeth, if you want. Divided by the square root of 40. Square root of 40.
I got minus 2.6.
Thank you, Alicia. Equal. Okay, I didn't get it, but anyway, you've done it better than I did. So how much was it?
Equal to 0,
Minus
like put H0 equals 0, the nu is always like H0.
H0 is mu of D equals 0, always. Yes. So
Oh, so
minus 5. I'm
the
just taking another scenario where instead of the 15, I'm taking 40. So to do it with the Z, okay?
Yeah, so Z would be minus 2.6
Okay,
in
great.
this scenario.
So so if I'm talking about 0.05, what is my Z, what's my Z critical? Minus 1.96 and 1.96.
On the outside.
So it is outside, right? So if I had a sample of 40 with a mean difference of 5.3 and all being the same standard deviation, the result would have been minus 2.6, and my decision would be actually to reject H0 rather to accept H0, right?
Right.
Okay, so the main difference between the two examples that we did is an issue of dependent sample, independent sample. How do
So
we
we
get
just needed more participants.
Yes, so independent sample, as I said, if we are we do a cross-sectional study. We collect data on the exposure, because when we say mu1 different than mu2, what do I mean different in sample? It means that people are different with respect to a certain characteristic. So for instance, if let me get a new slide, if I can have another slide. Oh, just talk, oops. I want to see a slide. So let me go. So here we have some space. Okay, so here we have two dependent sample. Again, that's example. I have the same people. Again, the dependent, I have the same people being measured twice. The same people. So if the people, for instance, have low on measure 1, they will be more likely to have low on measure 2. And you cannot consider these as two independent measures. Why? ليش مش independent measures? Because they are done on the same person. So that's why we call it dependent. But if I take N1 here and I do measure 1, I take a different N1, let's say male, and N2 female, N1 and N2, so 20 to 30 differently. Yani I pick up 20 males and I sample 30 female. I took measure 1 for male and measure 2 for female, male and female. I don't calculate a difference. I calculate mean 1, mean 2. So that's independent sample. Now, if I take 20 people, forget about this. I take 20 people, okay? The first person, so I select from the pool, from your class. So the first person is Nisreen, female, 18 years, okay? And I want to measure her BMI, okay? And I want to compare. So Nisreen, are you displaced?
No.
Okay, let's not talk about displacement with BMI. Do you exercise?
No.
No. So Nisreen, here is no. Okay, معلش I wanted something that's continuous, but nevertheless, let's say the outcome is exercise, yes or no. Okay, and then I want to compare exercise, no exercise. So my second would be, I pick up who's 18 years of age, for instance. So I pick up Lean. Okay, so female who's 18 and measured her BMI, but who exercise. So who exercise? Okay, and I compare. So now Nisreen is not independent of Lean. It's not I took a sample of people and I asked them whether you exercise. I take another sample and found them they are not they don't exercise. I match with respect to gender and age. One exercising, one is not exercising, and then I measure body mass index. So this is called match sample.
And these are
Okay.
dependent.
And
because
these
of
are
the-
exactly because they are matched. I cannot consider them independent, so I don't measure mean 1, mean 2. I look at the difference between Lean and Nisreen. So between Lean and Nasreen, and then between Faiz and whatever, another person, Muhammad or whatever. And then those differences, I can look at the average of differences and compare them to mu equals 0. So just be careful on the way the research is designed, because this will dictate how you will do the test of hypothesis to answer your research question, whether there is differences or not. If you do independent sample, that's fine. You collect all the data from the class. So to do it independently, I repeat, to do it independently is take a sample from the class of 203. You are 95. I take a sample of 40. I give you a short Google form. I ask you about age, gender, your body mass index, your weight, your height. Okay. And then based on the data that I find, I compare the body mass index between male, female, between age group, whatever. Okay. But if I select a group of female and then compare them to, let's say, male and female. So I take Nasreen, who's 18. I select another person who's female and who's 18. So one of them exercise, one of them doesn't exercise, and I take their sample. But the best example for dependent is when we do before and after. So either before and after or matched samples. Okay.